Friends, conducting this type of conference needs good financial assistance. And as a organizing chairman of financial committee, I am happy to say that we had a very good response in this direction from both government and private sectors. As mentioned by the organizing secretary, we had good representation in terms of sponsors from Ministry of Earth Sciences, Laurus Labs, they are the platinum sponsors, KLSR Infratech, Hyderabad, Serb India, the diamond sponsors, Kotak Mahindra Bank, LIC, Entupule Technologies, ANSYS, they are gold sponsors, and Ponala Foundation, Canara Bank, KME Projects Limited, Binary Cement, Maplesoft, DRDO, State Bank of India, they are the silver sponsors, and K4 Matrix, Warangal, University Warangal, Union Bank of India, Samay and Hamakonda, BAST India Limited, Anwar Ulum College, Hyderabad, Microtechnologies and HECO, they are the bronze sponsors. We heartily thank them for their generous contribution. And friends, for this type of mega conferences is not something that happens overnight. Months ago, the wheels for this conference began to turn. It necessitates forethought and keen eye for the detail in all aspects. I wish to express my heartfelt thanks to the organizing secretary, Professor H.P. Rani, Professor of Mathematics at NIT Warangal, who is like the backbone of this conference. Madam has put a lot of dedicated efforts in making this conference a reality today. In addition, we have been enough to have some team of proactive and dedicated members of our institution personnel, both faculty and student volunteers who are experts in their field. I am at loss for all to express my gratitude. I wish to express my thanks to things out there outside of the comfort. Professor of Mathematics. I wish to thank the three main pillars who have made this a reality. Madam has the majestic mathematics department. In addition, we have the Royal team of dedicated and dedicated of my personnel, both faculty and student volunteers who are experts in their field. I am extending my thanks to all the chairmen of different committees of the for making the arrangement. Most importantly, we had the good student volunteers. They are the resources of the marketing department, along with the mathematics, great round of applause. Thank you. I feel the department has the theme of this conference, which is the Indian theory and development. We complete I wish to thank Professor Richard for being Rahul, Chief Warden, Professor Richard I wish to give an applause for that. All those participants who travel from in this southern India, the state of Telangana, we have a word called the Telugu system. It means liking. So, అందరూ కూడా ఇస్లాం కాన్ఫరెన్స్గా పార్టిసిపేట్ means that will participate liking and love. May not be an exaggeration, and express on the validation functions. It is the 9th of December day or tomorrow. Jai ISTAM, Jai Ho and NIT Warangal. Finally, I would like to thank everyone here for taking the time to join us of this conference, which is held at NIT Warangal, and for assisting us in making this event. Thank you, one and all. Thank you very much. And express on the validation functions. December day or tomorrow.
Thank you, sir. Now I request everyone to rise for national anthem. Thank you. I request everyone to join for a photo session in front of old auditorium, followed by heights. Then there will be a presentation address by highest. So height will be arranged in the backs of Thank you all. I request everyone to join for a photo session in front of old auditorium, followed by heights. Then there will be a presentation address by So height will be arranged in the backs of Thank you all. Director for Deep Ocean Mission Project and Director at National Center for Coastal Research. Sir has joined online. Thank you, sir, for joining us today. Honor Professor I.S. Shivakumar, President of ISTAM, to grace the dais. To sir. Director for Deep Ocean Mission Project and Director at National Center for Coastal Research. Thank you, sir, for joining us. Now I take this opportunity to invite Professor Kumar, Secretary of I request Ms. Renika to present a sample to sir. Thank you, sir. So now I take the honor of inviting Professor Now I take this opportunity to invite Professor Secretary of I request Ms. Renika to present a sample to sir. Thank you, sir. So now I take this opportunity. Thank you, sir. Now I request Ms. Harika to present a sample to sir. I request Ms. Krishna Priya to present a sample to sir. Thank you, sir. It's my pleasure to invite our director, Professor Director of Varana to grace dance. I request Renuka to sample the sample. Thank you, sir. Now I take this opportunity to invite Professor Rani, Organizing Secretary of ISTAM 2023, occupy the dais. I request Ms. Harika to present the sample to us. Thank you, ma'am. Now I take this opportunity to invite Professor Rani. I request the gathering to rise our national song. I request other dignitaries on the dais kindly join. To give welcome others.
Good morning. As Organizing Secretary of ISTAM 2023, I take this opportunity to welcome the dignitaries, Professor Shivakumara, former Vice Chancellor of Bangalore University and President of ISTAM 2023, Professor D.K. Maiti from IIT Kharagpur and Secretary ISTAM. The guests, Professor Reshansky from Communist University, Slovakia, and Professor David from University of Tarapacá, Chile, and our beloved director Vidyathar Sudhi. And these HODs, other dignitaries, scholars, students, not the least, our beloved participants, who came all along the way from different parts of the country and also from especially from US and Kuwait. A warm welcome to all of you. I also take this opportunity to welcome on behalf of the organizing departments, mathematics, civil engineering, and mechanical engineering of our National Institute of Technology for the 68th Congress of the Indian Society of Theoretical and Applied Mechanics, ISTAM 2023, such as an international meet. This Indian Society of Theoretical and Applied Mechanics has started 1955 by the headquarters in IIT Kharagpur. So more about this we have displayed in the website also. This ISTAM attracts five special memorial lectures on the honor of B.R. Seth, B.L. Bhatnagar, B. Ganesh, A.S. Gupta, and G.I. Taylor, who are the eminent researchers from across the world, and also we have invited lectures which cover current and various topics of mechanics and also mathematics. The conference covers wide range of topics in the area of solid mechanics, fluid mechanics, and related experimental techniques. The response to the conference is overwhelming, as we have received several papers, out of which we have selected 208 papers, which are accepted for publication after peer review and presentation in coming days. The organizing committee express its profound thanks to the following organization for sponsoring the conference, especially the Ministry of Earth Sciences and the Ministry of External Affairs, who made it easy to welcome our foreign guests who are here. And the Laurus Labs, KLSR Infratech, GST Serve, Kotak Mahindra Bank, LIC, Enterprise Technologies and Answers, Bonala Foundation, Canara Bank, KMA Project Limited, Binary Semantics, MapleSoft, DRDO, SBI, K4 Metrics, HITS Varangal, SR University, Union Bank of India, Samaya and Company, BSS India Private Limited, Anwarul College, Microtechnologies, and HEICO. The pre-conference workshop was conducted by Binary Semantics for this conference. We are also indebted to all the invited speakers, authors from all over India for their valuable contribution to the conference. So today we will start with the presidential address by Professor I.S. Shivamala, followed by the plenary lecture by Professor M.B. Ramapurthy, the G.I. Taylor Memorial Lecture by Professor Rama Govindarajan, and P.L. Bhatnagar Memorial Lecture by Professor J. Wilson. So in the second day we will have B.R. Memorial Lectures, A.S. Gupta Memorial Lectures, and invited lectures also we have planned by Kishore Nath from DRDO, invited lecture by Professor Ajay Mulkar and Professor Sanjay Kumar. Invited lectures also we have planned from Yogesh, second day, that is tomorrow. Apart from that, in day 3 we have Karnesh Memorial Lecture by Professor Gautam Biswas, IIT Director, IIT Guwahati, who is a JC Boston Fellow in the Department of Mechanical Engineering, IIT. Also Professor Sriram Venkatesh from Department of Mechanical Engineering, University College of Engineering, Usmania University is also going to deliver the lecture. And Professor T. Pasak from IIT Madras, from the Department of Chemical Engineering, IIT Madras is going to deliver. And we have 2 more invited lectures by Professor Rajesh Swasana University, TK, and Professor Sergey Stachenko from Russia. These 2 lectures and one more lecture is planned in online. So apart from this, we have general body meetings, executive committee meetings of ISTAM. So we have 36 parallel technical sessions, 68 faculties, chairs and coaches. So those things are arranged nearby seminar hall. We ensure that almost all the presentations will be taken place. Also, we have arranged the cultural program which reflects the traditional dance of Telangana called Perini dance. I hope that all of you enjoy that. Followed by we have a conference dinner. And tomorrow we have planned for sightseeing. It will be announced on the website. So I request one more thing that all the delegates seek the blessings of Lord Bhadrakali and also Lord Shiva by visiting the 1,000 pillar. Also, I am sure that you will enjoy the marvelous architecture by the Kakatiya dynasty in the 1,000 pillar temple. If any lapses are here and there, please bring my notice. Otherwise, volunteers are there to take care of them. We hope that the deliberation pictures international meet results in fruitful outcome among the participants, enhance the field of mathematics and also applied mathematics. Thank you.
Dr. Karthik Subramanian sir to give introduction about the Secretary of ISTAM, Professor Deepak
Dr. Kumar Maiti, Professor Department of Aerospace Engineering, IIT Kharagpur since 2014. He got his master's and PhD from IIT Kharagpur. His thesis was completed in the year 1997 and was in the area of structure. To his credit, he has executed several consultancy projects, guided more than 15 students and published more than 15 international journal papers. He has personally organized 3 international conferences at IIT Kharagpur and has participated actively in several others. He has also been extensively contributed to the research of several doctoral students by being part of the doctoral scrutiny committee. Dr. Deepak is a life fellow of the Institution of India and a life member of the Aeronautical Society of India. He has been the Secretary of ISTAM since 2019, and now I invite Professor Deepak, Secretary of ISTAM, to give an overview of his
respected dignitaries who are in the dais, specifically head of the department mathematics, earlier head of the department, Professor Rani, and current head mechanical department, they have taken a lot of pain to organize this conference. Regarding the conference, actually, it rotates all over India, every year in different places. And last year, Rani has approached us he wants to hold in NIT Warangal. Finally, the committee agreed with that request. Next year also going to some other location. We don't know right now. But if we look back, this ISTAM started in 1995 with the guidance of ISTA and PRSL. Their idea was to bring the young researchers together and exchange their ideas. I hope as ancestors of our community, we are trying our justice, trying to give the justice to their idea. And in future also we will come forward to continue this. If you look at that way, the conference is mainly to exchange ideas and get interacted with your peers. So always I prefer that participants come physically interact because online mode or participation is not that quickly. During this COVID period, we could not organize offline or physical It was online. We have hold it, but if you look at that, it says we did had that feeling of organizing a conference like this. But with this physical mode, you have the opportunity, especially the young participants who are interested to continue their research in their area. They can get introduced to their seniors who are in a good position, who may get their support also. So when you are here, don't miss the opportunity to interact all the people whom you feel that may be helpful for your future career. And just to give you the idea that we have started our portal April 1st to submit the abstract, and then it was up to 31st July. Then we have extended 31st August, September. But thing is that even before 4-5 days of this conference, some people approached me, and we have allowed them also. Because basic idea is to have means encourage the young researchers. See, last time when we are allowing somebody at last moment, that makes inconvenience to the organizer. But still, we have tried our best to accommodate everybody. But despite of that, I still feel that would not satisfy all requirements. But you have to think from the organizer point of view that there are time required for such events, and making the arrangement. So always try to, whenever you are coming next time try to stick the time limit. That will help us to organize the more better way. With this, I thank you once again, and welcome to NIT Warangal for next 3 days. I hope that enjoying this program, whatever cultural program they will be conducting, and also the visits to the nearby places. See, that is a part of our life. When we are in research, don't try to get outside the research world. The conference gives you that opportunity, that is you have taken 4 days break, and you do other than your technical research area also. With this, thank you once again, and I hope we will be able to finally conduct the conference in a more rigorous and your experience. Thank you.
Now I request the dignitaries on the dais to release the proceedings.
Other than your technical research also. With this, thank you once again, and I Thank you.
Now I request the dignitaries on the dais to release the proceedings.
It will be available to view it. You can copy also. All the papers, first we have award-winning session papers, and then contributory papers. Both full-length paper and abstracts are available. please check it. If we have missed anything, please intimate me so that I can ask them to include it.
Sir Chandramohan to give the introduction of the chief guest of ISTAM.
All the papers, first we have award-winning session papers.
So, Dr. M.V. Ramanamurthy, Director and Scientist, National Center for Coastal Research, NCCR, Ministry of Earth and Science, Government of India. He has educational qualifications of BE Civil Engineering in 1987, Nagarjuna University, India. Tech Planning Department, School of Planning, CEPT, Ahmedabad. Tech Ocean Engineering from IIT Madras in 1997. And PhD also from IIT Madras in Ocean Engineering Department and completed January 2008. He has a vast experience. He started as a senior engineer, Trust, and served from 1991 to 1997. Senior engineer, India Limited, Bangalore, from 1999 to 1999, and then signed D. Scientist TF, DOD from 1999 to 2009, and then signed TF, National Institute of Technology, Ministry of Earth and Sciences from 2019 to 2017, and he served as a scientist and group head for ocean structures and island desalination, National Institute of Ocean Technology, Ministry of Earth and Science from 2013 till today, and then he is the Director of National Center for Coastal Research, Ministry of Earth Sciences, Government of India. He has lots of achievements, so I have taken a few here. He has customization of phenomenal model for early warning systems such in Koi, beach restoration, Pondicherry and Kadalur, Tamil Nadu, Chennai flood warning systems, sea flows, establishments of desalination plant and pilots for 8 islands, sealing between Port Blair and Rusland for drinking water supply, feasibility studies of offshore India and Tamil Nadu, like that. There are lot of achievements he has done, and he has lot of awards also. One is National Geoscience Award, outstanding contribution in the field of disaster management from Ministry of Mines, Ministry of Earth Sciences Award in 2006, outstanding contribution in the coastal process modeling. American Bureau of Shipping Award for Department Outstanding Department for his outstanding of 9.88 for M.Tech Engineering IIT Madras. Merit Certificate Chairman for outstanding contribution in integrated sports and cultural complex. And then he is a lot of membership in number of societies and bodies. And also he has more than 40 publications in national and international research journals, 50 plus publications in national proceedings, and more than 20 plus technical reports, and then 45 plus delivery track. We are happy to welcome him, Professor M.V. Ramanamurthy. Thank you. And then he is a lot of membership in number of societies and bodies. And also he has more than 40 publications.
Okay. So to be fixed somehow.
They are fixed, but I think we are audible to them. Their audio is not.
So it will be possible to hear the audio from the meeting?
Yes.
Oh,
Plenty of planets, I think.
But did meeting actually started or not?
No, they started, then they are all off.
Okay. But they started already.
Yes.
Let's try to let's hope that
I request M.V. Ramanamurthy to address the answer.
Before I speak.
I hear you.
No, I'm just checking that conference.
But did meeting
Yes. Am I audible?
Yes, sir, audible.
Yes. Very good morning to all. Professor Shivambaran, President ISTAM, Professor Sudhiri, Director NIT Warangal, Professor Deepak, Secretary ISTAM, and Professor Saki, joining online, faculty, students of NIT Warangal, international and national delegates, ladies and gentlemen. It gives me immense pleasure that National Institute of Technology Warangal is organizing 60th Conference of Indian Society of Theoretical and Applied Mechanics, so-called ISTAM 2023, during 7th to 9th 2023, to provide a platform for scientists, technologists, and engineers to share and discuss current research conducted by them in seeking solutions to emerging problems for better living conditions. It gives me immense pleasure. It is really unfortunate that I could not attend this conference in physical mode due to the cyclone caused by damage in many parts of the United and impact my office surface and water. The themes of the conference address various topics on mechanics and soil mechanics, which are very providing solutions to engineering problems, and also resources which I am coming from, such as earthquake, landslides, tsunami, extreme weather, climate change, such as floods, urban floods, and also ocean disasters, and also land based hazards. It provides an opportunity for researchers, engineers, scientists, specialists in various areas of development of engineering and technology related to applied mechanics for the benefit of society. Having worked in the area of science and engineering, I strongly feel that recent advances in computation and applied mechanics will help understand the various processes to evolve innovative technologies in manufacturing. While I was working with offshore technologies, I came across many problems that can be solved using computational dynamics and numerical modeling. Recent advances in computational power, virtual reality enabled us to solve many problems. One of such ideas was to develop an offshore numerical tank to aid design of offshore vehicles. Similarly, we all know about climate changing, and then we have many problems. We have on both sides. One side of the disaster, another side adaptability for the climate change. We have a system model developed by Center for Climate Change Research located in IIT Pune to simulate air system process, flood warning systems, and also disaster management. I hope eminent speakers in this conference will cover things from different perspectives, from theoretical aspect to application. We know very well that applied mechanics, both theory and its application, is very valuable and immense help for the many day-to-day problems. I'm pleased to say that this conference will definitely offer solutions to simulate air system process, flood warning systems, and also disaster management. I hope eminent speakers in this conference will cover
mathematics, Dean Faculty of Science Engineering, Bangalore University. Professor Shivambaran was born in a village in Tumkur in Karnataka in 1957 and took his BSc in 1977, MSc in 1979, MPhil in 1982, and PhD in 1986 in fluid mechanics. All the degrees from Bangalore University. He has been a prolific researcher and a magnificent teacher, having started his career way back in 1980. He has close to 4 decades of both teaching research experience. His research contributions is evident in the PhD thesis guided, which is number 26, and MPhil, which comes to 9. He has an enviable number of papers, 265 to his credit, and in national and international journals. Professor Shivambaran has been cited 3,016 times and has a H index of 32 and I-Titan index of 110. These are really noteworthy credentials for a man who is renowned as much for his scholarship as his administrative capabilities. Professor Shivambaran was Vice Chancellor in charge Bangalore University. In 2018, Dean Faculty of Science, Bangalore University. Dean Faculty of Engineering, Bangalore University. Director, HRDC, Bangalore University. Chairman, Department of Mathematics, Bangalore University. And UGC CAS program coordinator, Department of Mathematics, Bangalore University. Registrar, Tumkuru University. Director, Tumkuru University 2005. Director, PG Center, Tumkuru. Deputy Coordinator, UGC CAS program, Department of Mathematics, Bangalore University. Member of the Committee of Indian Society of Applied Mechanics. Secretary, Central College Mathematics Society, Bangalore University. Member of Studies of Mathematics, Bangalore University. Professor Shivakumar is the founder of Indian Society of Industrial and Applied Mathematics. He is a member of Indian Society of Applied Mechanics. Besides, he was elected as executive committee member of ISTAM for 3 years from 1999 to 1999. He is a member of the National Academy of Science, Allahabad, India. He has been the recipient of many awards, starting with President of India Award for the best presentation at the 26th Congress of Indian Society of Theoretical and Applied Mechanics, which he won twice, once in 1981 and second time in 1982. He was then conferred recipient of Young Scientist Award instituted by the Karnataka Association for Advancement of Science in 1986. Professor Shivakumar was elected fellow of the National Academy of Sciences in India 2001. He was bestowed the ISTAM National Harihom Ashram Trust Award titled Meghanand Shiva Award for outstanding contributions on theoretical science in 2010. He had the honor of being nominated by the Department of Science and Technology, Government of India, New Delhi, as an expert from India to deliver and talk in the International Conference on Applications of Fluid Dynamics organized by the University of Botswana in 2012. Professor Shivakumar is recognized among the top 2% of scientists from India in the survey conducted by Stanford University of USA, and his contribution was recognized in the field of mechanical engineering and transport 2020 and 2021. The professor has visited as many as countries to deliver lectures, take part in seminars, workshops, these being the USA, Singapore, Canada, China, Korea, Germany, Botswana, Hong Kong, and so on. Professor Shivakumar has edited 8 books, organized 28 international conferences, 29 national conferences, 17 workshops, and delivered a great invited talks and lectures. Professor Shivakumar resume is indeed highly impressive, and I am delighted to introduce such a brilliant keynote speaker to the audience, and I extend a very warm welcome to him. Thank you, sir. Professor Shivakumar has edited 8 national conferences, 29 national conferences, 17 workshops, and delivered a great invited talks and lectures. Professor Shivakumar resume is indeed highly impressive, and I am delighted to introduce such a brilliant keynote speaker to the audience, and I extend a very warm welcome to him. Thank you, sir.
Good morning to all of you. My clients are young researchers and all others, please excuse me. Is it audible? Okay. Thank you, sir. So the title itself shows it is a bird's eye view. Therefore, I don't expect from the chairs to follow whatever I say. No, of course, it is not my intention either. It is very difficult to follow whatever we talking now.
In fact, there are some words in this one. I can see that. Stability is just a usual English word. Stability. Often we use the word stability by everyone. Even individuals also speak about stability of a person. So they are not financial and political stability, or stability of stock market. We talk stability of vehicles we speak, and so on and so forth. Always will be using this word. So I think one can speak about stability of flows also. It is not an exception. So what is that we are going to speak about stability of flows? Madam is here, Professor Raman Rajan. She is an authority in the field of stability of flows. But here we are going to discuss a different type of stability of flows. Whenever there is a fluid flow means, why? Due to what? There may be different types of forces. So due to that there is a flow. For example, pressure gradient force, shear force may be there, or buoyancy force is there. Because of that, flow may occur. But here I am concentrating only on buoyancy driven flow and the stability of flows. Okay. So how we are going to study stability of flows in general? Okay. So stability of flows are discussed. First of all, stability of any system for that matter, we have an initial system or initial flow, or it is also base flow. So on that we are going to superimpose some small disturbance or large disturbance, whatever it may be. But I am discussing only on small disturbances. So some small disturbances are imposed on those base flows. Then we are going to see what will happen to these disturbances as time progresses. Whether these disturbances grow with the time, then we say it is unstable, or decay with the time, then we say it is stable, or it neither grows nor decays, then it is stable like that. Do it. But usually all the disturbances are going to vary spatially as well as with respect to time. That is how we are to do it. Okay. So that is what I am going to discuss now. We can see that. But as far as the stability of viscous shear flows concerned, they are very classical field of research. In fact, the stability of fluid, studying that is a classical field of research in fluid mechanics. So for the last, I think more than a century, that field of research is still active. People are working. Okay. So now I'm just would like to mention two important names as far as the stability of viscous shear flows are concerned. For your information, just to give you these two names. Those two important scientists are first one is Bohr. Another is a mathematician, Bohr. The next one just call it Sommerfeld. He is an applied important name as far as the stability of viscous shear flows are concerned. For your information, just to give you these two names. Independently, this equation. So Bohr derived in 1907. Sommer derived in 1908. They were not knowing he has also worked on the same problem. Even he has worked on the same problem. But later on they came to know that both of them have derived the same equation. That's why in the literature later on it is called Bohr-Sommerfeld equation. It is a well celebrated equation as far as the stability of shear viscous shear flows are concerned. So it is a fourth order differential equation. See that with the complex coefficients and the boundary conditions. They have derived for many years. They have tried to obtain very good results. That means numerical results because analytically it cannot be solved. In fact, they said that when the base flow becomes unstable, that means the base flow becomes unstable means there is a transfer of energy from base flow to the disturbances. Therefore, the disturbances grow and the flow becomes unstable. Here in the flow problem, unstable means first the flow will be laminar, then it becomes turbulent. So what is the value of the Reynolds number means they have given 577.2 something. Okay, if it exceeds that value, then the flow becomes laminar to turbulent. That is the understanding. But you know that there are interesting facts about Summerfield. He was nominated for 84 times for Nobel Prize. 84 times, I don't know how it was possible, but it is there. Okay, if you look into it. So, but he didn't get Nobel Prize. But 4 of his students got Nobel Prize. Who are they? So one is, we have written Heisenberg, uncertainty principle or something there. Pauli's principle, he also got Debye and other things. They went on, getting Nobel Prizes. 4 of his students. That's why I'm telling you, young researchers. So you can work better than your research advisor. It is possible. I think much more better than your mentor. It is possible. That's what it says. I think you can always work in that direction, friends. But I told you, not this type of stability of fluid force I am discussing, but now I am discussing only the flow is due to buoyancy forces. So I have considered some geometry. Okay, in that time, whatever we are doing at present. So this is the geometry that we have considered. That means we are having a vertical porous layer. You can see that. So it is filled with porous material. So the boundaries, you can see that they are at different temperatures. Okay, one is greater than the other, and also the gravity is acting. Because of this, basically there will be a parallel flow. There exists a parallel flow because gravity is acting because of the buoyancy forces. So there is a parallel flow here. So now we are going to discuss the stability of this one. But who was the first person to discuss this problem? So all those things I am going to show. So how the things have been occurred with the time based on this problem. Okay. So the equations, everything, because I am a mathematics student, I will also show some equations. Simple equations. What are those equations? Basic equations and other things. The next one. Okay. Please remember this man. His name is Gill. A.E. Gill. Okay. In 1969, he worked on this problem. Actually, he discussed stability of, I think something, this is nothing but natural convection in a vertical porous slab. So it has appeared in Journal of Fluid Mechanics. Just you also see, this is the shortest paper ever published in JFM. That's what they write. It is just one sheet paper. That's all. 2 pages. Just this side, that side. Another page, there are only 4 references are there. That's all. Okay. It is the shortest paper ever published in this one, but you can see how many works have been done on this particular study. Okay. What are the equations? You can see just very plain looking equations. These are the equations which we have written in the dimensionless form. So we have considered the lossy momentum equation. You can see that usual temperature equations. And here we don't get the Reynolds number because the buoyancy driven flows. We get the corresponding number that is called the Rayleigh number. Is called Rayleigh number. So based on that we are going to discuss the stability of flows, not on the Reynolds number. The boundary conditions are very simple. You can see that the velocity component perpendicular to the planes, that will be 0, and other things we have done it here. Okay. So we are interested in studying what is the So there are so many things in this one. I don't want to dwell upon that because there is a square theorem. Very celebrated theorem. What it says means two-dimensional disturbances are more unstable than three-dimensional disturbances. That is called square theorem, which has been proved. For many stability of fluid flow problems, they derive that theorem. So that theorem is valid for this. Therefore, we have considered two-dimensional motions in terms of stream function we have written. This is the base flow actually. This is the base flow. So basic velocity. This is the disturbances. That means we have to write down the equations for the disturbed quantities. Finally, we write down. So we disturb that whatever the flow is there, like this disturbances. They are all functions that affect T. You know that these disturbances are regular functions in space variables. Regular functions means they are continuous, differentiable, bounded, all those things are there. Therefore, always we can put them into Fourier modes. Fourier decomposition we can do it because they are all regular functions. So we write down the equations in terms of these disturbed quantities and this is the normal solution or the Fourier decomposition we do it. A function of x and exponential of these things. Okay. This is the quantity we are interested in. C is usually a complex quantity because as we have multiplied, we see actually exponential of some complex quantity depending upon the real part, imaginary part. Real part is very important because whether it goes with time or decays time, we can analyze that. So similarly we can see that here if Ci greater than 0 it becomes stable, less than 0 the quantity becomes stable. All the perturbations decay. Therefore we can talk about so the flow becomes stable. This is how we are going to analyze it mathematically. Okay. Any stability problem. This is how we do it. So even another way also even our common sense that if at all you want to see any system stable or not, you disturb that system. What will happen to that system? We can see and accordingly we can analyze whether it is stable or unstable. That is what we can do it. This is what we did it. Okay. But here what is the method used? In fact, in almost all stability problems, what you have to find out means e to the power of some quantity C times T is there. That is a complex quantity which we have to determine. That is the eigenvalue. That is the eigenvalue as far as the stability of fluid flows are concerned. We have to determine that. Either we have to determine analytically possible, otherwise we have to determine numerically. Only two things are there. So now what he did, that is very important here. Finally these are the equations we end up. Okay. So if we put that normal nodes and everything, we get these two insane looking ordinary differential equations with complex coefficients. Okay. Second order. It is possible boundary conditions like this, but we can eliminate. It is possible to eliminate psi from equation to just you operate by d squared minus s squared. We can do that. Okay. Because there are constant there are some variables also there. But anyhow we can do that. Okay. You operate on that. Therefore we can get a single equation involving theta. So this equation, I think it is not a Moore-Sommerfeld equation here. It is only a type of Moore-Sommerfeld equation. Here also you can see that it is a fourth order differential equation with complex coefficient, but it is not a Moore-Sommerfeld equation. It is just a stability equation we can say. So this equation we have to solve because C is there, you can see here. That is the quantity that we have to determine. But what he did, He used an integral method for this one. What that method? Just you multiply the equation by the complex conjugate of that temperature. Then integrate it by parts across the thickness of the porous layer. Then what is that we are going to get it? I think we are written here. So this is the equation, finally we will get it. You see, this is a perfect equation. That means this is a positive quantity. This is everyone here. Then we have to equate real and imaginary parts. We are interested in the real part because e to the power of c times t means so real part means it grows. If it is negative, positive, depending on that we are going to discuss the stability of flows. So now equating the real parts on both sides. You can see here. So if you write down this one, negative of the entire quantity. This is positive modulus, this is positive, this is positive because A is the wave number of the positive quantity. Everything is positive. Ci less than 0. That's why it was just a two-page paper. He said that for this type of problem, the flow is always stable. The base flow is always stable. That is the important result that he put forth. So he said that a stationary parallel flow is always stable to all types of disturbances for all values of the Darcy-Rayleigh number. This was considered to be a cornerstone result as far as stability of natural convection and vertical porous layer is concerned. That means what? It is stable. Stable means there is no heat transfer. The heat transfer is only by conduction, not by convection. That means there is no heat transfer from the base flow to the disturbances. Therefore, the flow will be always stable. That is what he said. And also he made why this problem was so important. Okay, so even technologically, why this problem was so important means he made a statement, one statement. That statement was the problem, whatever he has done, it is of importance because this idea can be used in building insulation. Okay. Where they are using air gaps. In building insulation, they are using the air gaps. But his study is much more relevant whenever they are considering building insulation. What is that building insulation? What they are using? What they observed? Why his study was so important in that one? Okay. That is what he wrote. Just 2 lines. He wrote that one because his problem is important in connection with the building insulation. Okay. So what is that building insulation? You know that I think in Western countries it is very cold. They are heating the buildings so that they want to keep the temperatures. Okay. They have to regulate that one. Therefore, there should not be any heat loss or gain into the inside the building. That is what they are going to do it. So in what way this one will be useful? Just I took out of interest this one. How they are going to do it? Building insulation. I think you can see here. This is the outside wall. And also inside they are using some insulating material. In between these two, they are having some air gap between those two. Why they are having air gaps means air is not a good conductor of heat. So this air gap, whatever they are leaving, it acts as an additional insulation layer, so that they can have a better insulation of the building. That was the idea. They are doing it. But what they observed means same people have discussed later on. What they observed is whenever they are having an air gap here inside. There is a temperature difference. Actually, this air gap which acts as a buffer between the inside temperature and the outside temperature. So it helps in regulating the temperature inside. So that is what they said. But they found out that whenever the temperature difference across this air gap exceeds a certain width of the air gap, then cellular convection occurs. That's what they observed. Cellular convection occurs means heat transfer increases. Therefore, it is not viable to have only air gap. So something we have to do it. So his study, Gill's study, what they said that if we use the porous material instead of the air gap, then he has put forth that there will be no instability. That means there is no transfer of heat across the porous layer. Therefore, it will work as a better insulation than having only air gap. In that way, his work was much more superior, considered to be breakthrough as far as the building insulation is concerned. That's what he wrote, only 2 lines. So in such situations, his results, whatever he got, because there is no instability, that means there is no heat transfer across the porous layer, therefore it works better in the insulation of buildings. That's what he said. Therefore, that work was considered to be, always everyone writes, a pioneering work by Gill. That's what they mention always. It was a cornerstone result. But I am telling you, even this was questioned by many people later. How many years it has taken? Nearly 50 years. So that's what I would like to tell you. So don't think that only 3 years back, 4 years back, what they have done. Even you can go back and you can see. After 50 years back, some other person came and he said, what is that? So here, whatever the boundaries considered Gill, it was impermeable boundaries. Between impermeable boundaries, there is a porous material. Whenever we are having impermeable boundaries, then what will happen? Nothing goes in and also nothing comes out. Then what will happen? Inside, for the better air quality within the room or within the building. So we have to reduce the concentration of the air pollutants. How to reduce the concentration of the air pollutants when it is not going anything outside or fresh air is coming in? Then the concept, the novel concepts that were introduced in the building insulation was breathing walls. They are called breathing walls. What is the breathing walls means? Even walls breathe. Means what? Something it will take in and goes out. So such concept was introduced. If at all we want to introduce breathing walls concept, then we can't have impermeable boundaries. It is highly impossible. Then he put forth that instead of impermeable boundaries, one has to consider imperfectly impermeable boundaries or partial permeable boundaries. It should be. Then only it will allow the air to flow outside or something comes in. Therefore, we can reduce the concentration of the air pollutants inside the building. It is possible. Then what he did, he reformulated the same thing. What he did, no, one consider permeable boundaries and let us make a study. So this is what it was done. You can see in 2015. 2015, I think they are stalwarts in this field, always so many, I think, works you can see. In 2015, how many years? After 46 years of that study, so he considered this one. So instead of considering the impermeable boundaries, how the permeable boundaries will work on such a study. So he has also published the paper in Journal of Fluid Mechanics. What is he did? Friends, I am telling you, mathematically it is nothing. You see, he considered the same equation, same base flow, same equations. Just instead of psi, he put d psi. See mathematically what it is. Instead of psi, it is only d psi. That considering dpsi made so many things. Mathematics is complicated. Earlier it was a mathematically telling Dirichlet conditions. Now it has become Neumann boundary conditions. Find the solution. He said that whatever the analysis done by Gill is not possible to extend. The first thing. The next thing what he did, he solved it numerically. Okay. He solved the problem numerically, everything. Then what he has done, just we have written. From permeable to, from impermeable to permeable makes the base flow unstable, other way. Okay. From impermeable to permeable, what he said means, no, there is a possibility of base flow becoming unstable. That means there will be a heat transfer by changing the boundary conditions. So when he also gave that number, what is the Darcy-Rial number is 197 point something, some Reynolds number, what he said, here he said, once it exceeds, then there will be an instability. This is what I am going to tell you, friends, researchers. Why means this is how we have to think. Okay. So always you think that what type of problems we are doing and what we have got. Always that is most important. That means some standard results may be there already in the literature. But how we can contradict by considering the situations which are very much relevant to that problem. We should not contrive something in our mind and we should use. No. It is demanded. Why he considered permeable boundaries? Because the situation demands that. He considered that. And he showed that the same results will not be valid whatever Gill showed earlier. Okay. So instability is possible of that base flow. So he published, that's what he wrote down. Just see its title. A proof that slab may be unstable. Rather than becoming always stable, it can become unstable, he said, and he published. Okay. Are there any other situations? Are there any other situations which demands that this problem can be analyzed by considering other aspects? What are the situations that will demand, okay, in discussing such type of problems? That can also, one can look at. It depends on your thinking. That is what it has. So, young researchers, always you have to think, you have to see, foresee, oh, these are the situations which demands these things. Okay, next, others thought about that one little bit. What is that? Whenever we are having a porous slab, it is very difficult to have. When we have the permeability, here what they consider, the permeability of the porous medium is constant. But even man-made porous materials you take or naturally occurring porous materials you take, it is very difficult to visualize. We will be having only constant permeability because the packing will not be so perfect. Always there will be chances of being, what is that? Heterogeneity in permeability. So one can think of that one. Okay. There will be heterogeneity in permeability. How about looking at this problem, considering heterogeneity in permeability? Because many people might have done other things. But how about visualizing the Gill's problem? Because he has said always it is stable. So our aim is to see that under what situations his result will not be valid. How to contradict that result? Because it is a standard result. So the next authors thought about, how about considering the heterogeneity in permeability? Heterogeneity is what? It is the permeability, it is where permeability means the ease with which the flow takes place in the porous medium. So how it can vary? In different ways it can vary. It may vary linearly, or it can may vary quadratically, or it can vary exponentially. There are different things. So how about analyzing that problem, because the situation demands that? Okay, how about analyzing that problem by considering these things? This is what the next authors did it. You can see. I am also there in that. Okay. So what we did means we consider again that thing, heterogeneity in permeability. Again it appeared in Journal of Fluid Mechanics. Friends, you see, there is a result. We are always contradicting that under different situations. That's what we are doing, that's all. So take this situation which demands, that is not happening. All of that one. We did it in 22. After how many years? 53 years. See, 53 years back the problem was discussed. Now we are telling it will not happen. Whenever you are choosing problems, you have to see standard journals, what they have done. Are there any situations which we can look at it in a different perspective? And can we get some different results? Always we have to do that one. Okay, so we did that. So here K is not a constant. We said that it is varying across the width of the porous layer, and we considered different aspects. Okay, but here the stability equations are a little bit different, and we considered linear heterogeneity. Then the base flow also changes accordingly. Then we considered quadratic heterogeneity. The base flow also changes accordingly for that one. Then we consider exponential heterogeneity, all possibilities, linear and non-linear heterogeneities we considered. This also we cannot solve it analytically, we solved numerically. Then we found out that possibility of base flow becoming unstable again. That means whatever the results put forth by Gill will not be continued for this type of situation again. Okay, so we consider heterogeneity, and we all discussed when, for what values and all those things. There are details in that one. You can see that. So anyhow, totally this is the result. It becomes unstable in this situation also. So again, you see how the people will be thinking. They thought in a different way. What is that? The heterogeneity was continuous across the porous layer. But another person, now you can see not one person, many people, they discussed it in a different manner. Same heterogeneity, but they discussed in a different perspective. What they did it, this one you take. They considered instead of one porous layer, it is supported by other two porous layers, but this porous layer are having the same physical properties, but the core porous layer is having different physical properties from that of the. So here it is having one permeability, this is having another permeability, this is having the same as this permeability, but you can see that heterogeneity also here mentions, he writes, so and so have considered continuous heterogeneity, but we are considering here a different type of heterogeneity because the permeability is here something, here it is different, it is a piecewise heterogeneity. Piecewise heterogeneity in permeability. So this was also considered by Barletta and his students. This paper has also been published in JFM. Same continuously it is going like that. Okay? Only take the situations, look at the Gill's problem. No, his results will not be valid under this situation. Only these things they are doing. Okay, always. So he showed that the flow becomes unstable even in this case because this is mathematically complicated because of the interface boundary conditions and all those things. It is very complicated thing. But anyhow, they solved and everything numerically and showed that this becomes unstable. So the next thinking, what is the best thinking, next thinking? I was going through Professor Rama Govindarajan's paper, which is a review article, JFM, Journal of Fluid Mechanics review articles are there. Okay, so I was just, I came to know that paper, he was telling. Only I saw the paper because other things really we cannot, it is not our cup of tea. It is a very technical things will be there I told you she is an authority in that field, stability of fluid. She has mentioned what is the role of viscosity on the instability of fluid flows. Has written, okay, it varies spatially and also with the time also something, and everything with the temperature, so many things are there. Okay, why can't we look at the viscosity, which will be a function of temperature, because it is a thermal convection problem. Usually it should vary. And also experiments show that the viscosity varies 20 times faster than your thermal conductivity. So even if you don't consider the variation in thermal conductivity is not a problem, but viscosity varies drastically. So we thought of, okay, why can't we take the viscosity varies with the temperature. So this is what we did it in the next thing. So we considered viscosity varies in a different way. I think how it can vary linearly, they say, quadratically, say, exponentially. So many variations are there in the literature. How it will. So we discussed this, for example, quadratic variation, exponential variation, everything. Then all those things we read. For one type of variation is stable, that means whatever he has done, Gill follows, but in the other case, it is not. This is what we did it. Okay? So we could able to publish that also. Like this, only on Gill's problem I am telling you, 1969 paper, it has been churned. Okay? So, and they have derived so many things out of it. Okay? So how it varies, how it changes under different contexts, and this is what they have done. Okay? So many things, so many people are. He is also that D.A.S. Rees, he is from Bath, University of Bath. Oh, he is also a stalwart in this field. He has also done. But there what they have done means it is not changing under different situations. But always you have to show this one. You have to contradict some standard results. Then only it will be having, more weightage. Same thing it is happening means, okay, it is not that much interesting. You have to show that it is something different from that. Okay, so it is stable. Yeah. Then they consider non-Newtonian fluids also. They discussed. Okay?
Yes, sir.
Okay. So other things, they consider power law fluids, things like that. We consider Woodwright B fluid. Again we published. Okay, something becomes unstable. So, thank you. This is what I wanted to present. But the only thing is I want to tell our young researchers, that means always there is a need to look at the research problems properly. You see some standard, journals you have to see. Even if your paper is rejected, no problem. At least you will get some good feedback, you will get it, so that you can improve your study. So instead of that one, don't go behind predator journals. We should not do it. We should not go behind predator journals. Even if you don't get publication, doesn't matter. But the sad thing is, our education policies, madam is here, I don't know where they have to bring it. Because of that, the research has been spoiled. In fact, I am telling you, madam, it has been spoiled because whoever comes, how many papers you have published? How many papers you have published? How you can publish? If you send a paper to a good journal, it takes 6 months. Here, 2 months, 1 month, one paper. How we can do it? Only they have to go behind such a thing. Because they are asking these things, what is that you have done, what is that you have done, because our policies, it has been spoiled, actually, the research, mostly. So such a thing should not happen, but always you try to look for good journals, good work, then you try to do something. Okay, it takes time, doesn't matter, you do it. But I know that because I am from the university, we know it, what are the problems we are facing to do research. in the university setup. I think IIT people, NIT people, they don't know. Even I cannot download my own paper for your kind information. I am telling you, I think recently one girl, I think from NIT, Delhi, she asked me one paper. I don't have. Then after 2 days, sir, no, I got it. I have got it through some means. How she got it? Then you send it to me. I asked her, because this is the situation in the universities. Forget about other things. Okay, this is the situation we are feeling, we are finding in the universities. So in that one, they are doing really hats off to them, our university and other engineering college students, because they are struggling very hard. They are not getting fellowships or anything. Simply they will be working on their own. It's a difficult task actually. This is what I wanted to place it before you, how we can look at the research in a different perspective and we can make something out of it at least. That is what we are all doing. I think you can also do it. Thank you. Thank you for your patient hearing.
Thank you, sir, for a wonderful lecture. So, due to lack of time, so we are allowing to ask the questions. Please, we will provide the email IDs. Please ask through mail. Yeah. Afterward, sir is 3 days here. He will be here so that he can interact. Okay. Thank you very much, sir.
Thank you, sir. So now I request Professor Suresh Babu, sir, to introduce Professor Rama Govindarajan, the speaker of G.I. Taylor Memorial Lecture.
Good afternoon, everyone. It's my pleasure to introduce today's the speaker, Professor Rama Govindarajan. Madam has currently working as a senior professor at International Center for Theoretical Science, Bangalore. Madam has been graduated from the BTech Chemical Engineering, IIT Delhi in 1984, and also won as Distinguished Alumni Award for the year 2022. Madam has acquired her PhD in the area of aerospace engineering from ISC Bangalore and also won as a Platinum Jubilee Prize from this department in the year 2017 and also completed her postgraduate PDF from California Institute of Technology. Madam pursues the research in the area mainly focusing on the fluid mechanics, where fluid dynamics is being the main area. Works in the area of
So what this is plankton in the ocean. So how many of you heard about carbon sequestration? Carbon sequestration as a thing for climate. So basically these phytoplanktons, very small organisms in the ocean, they actually grab carbon from the atmosphere. We are the bad guys who put carbon in the atmosphere, right? And we create, global warming and stuff like that. But these little guys, I mean, they are so small, and on their tiny shoulders, it is responsibility of grabbing the carbon and taking it down to the ocean, and taking it down to the bottom of the ocean. So they actually mitigate the effects of climate change. So these guys are very important to us, marine snow. And so how they cluster, how they go down, that becomes extremely important, because the rate at which things are carried to the bottom of the ocean depends on clustering. Similarly, in clouds, clustering is very, very important, because if there was no particle clustering or droplet clustering, there will be no rain. I know that the last 2 days it's been raining out here and everybody is worried about this meeting, so you didn't want clustering. But on normal days you want clustering and you want rain. So you need droplets to come together to grow bigger. So what we're going to be looking at is the easiest case, where we're talking about particles in dilute suspension. So here is this flow with some typical velocity field u, and the particle velocity I will always call v, and the flow velocity is u. So there are particles who are not quite going at the same velocity as the fluid. So they could be even big rocks or going in their own way. So, but we are not considering big rocks, we are considering very tiny particles in very dilute suspension. Dilute suspension means one-way coupling. That means that, okay, imagine it this way. So suppose there are a bunch of bacteria sitting in the ocean. Then the ocean will tell the bacterium where to go. The bacterium will not be able to do anything to the ocean. That's what we mean by one-way coupling. These are too small to affect the flow. So the flow still goes by Navier-Stokes equation, and being ocean, atmosphere, or some big dust storm or something, the Reynolds number for the flow is extremely high, and the flow is incompressible. Particle is not incompressible. This is important. The flow is incompressible. So we are now looking at high Reynolds number for the flow, and the flow doesn't care about the particles. That's the easiest case, and we're going to talk about that. And like we could run big simulations with many particles and get many results, but then we won't understand what's happening. So our aim here is to make it simpler and pare it down to the simplest thing and see if we can write something analytically, if we can write something with simpler equations. So given that, we look at this slice of two-dimensional turbulence, and Rashmi Ramadugu, I forgot to put her photo here. So she looked at typical samples of two-dimensional turbulence, and she looked at, okay, so in turbulence you have this velocity field u, right? The curl of the velocity is what? Vorticity, right? So like we look at vorticity. So you just plot the curl of the velocity here, and you'll see that the vorticity is usually concentrated into patches. Not only is it concentrated into patches, she looked at a few of these and she plotted their profiles, and it's always Gaussian. So these are Lambosine vortices. So very often in 2D turbulence it's very Lambosine, in 3D it's distorted Lambosine. But Lambosine vortices are pretty good model for turbulence. So when we're looking at particles, these particles are extremely tiny, right? Remember I told you, let's think about bacterium in the ocean or something like that. For them, this vortex is very big. So these particles are going to be just in the influence of one or two vortices. So why not just take one vortex which has this kind of velocity field, and as delta tends to 0, that's the thickness, it goes to a point vortex. So why not do things with in the neighborhood of one vortex and particle? So that's the idea we started with. And now I told you the equation of the fluid, which is Navier-Stokes, but what's the equation for the particle? So inertial particles, which are heavy particles in fluid, like imagine water droplets in a cloud, they obey this very simple form of what is called the Maxey-Riley equation. The Maxwell equation was written for unsteady Stokes flow of a particle. The fluid is in very, very big Reynolds number, but the particle Reynolds number relative to the fluid is very, very small. So this is V minus U, which is the relative velocity of the fluid and particle, and based on the radius of that teeny tiny particle. So this is the kinematic viscosity. The Reynolds of the particle is very, very small. So we live in unsteady Stokes flow, or sometimes even in steady Stokes flow. That's the limit we are going to be talking about. One of the important parameters for us is the Stokes number. The Stokes number is the time scale of the particle divided by the time scale of the flow. And A is the radius, mu is the kinematic viscosity, T is the time scale of the flow, rho P and rho F are the two densities of the particle and the fluid, and this quantity also will become important to us. Now, this is the simplest Maxi-Rayleigh equation. X dot is V, that means the particle's position translates according to its velocity. Its acceleration is given by this equation. And now, this becomes what is called a singular perturbation problem. So what is a singular perturbation problem? Everybody's heard about regular and singular perturbations? Can you raise your hand if you have not heard about a singular perturbation? Okay, so yeah, a few people. So it's very easy, like I can just tell you in one sentence. So this is a second order differential equation, correct? And I could have a particle which is very, very small, its radius is very, very, very small. So Stokes number is very small. So suppose like I am confronted with an equation where let's say this guy is epsilon and epsilon is 10 to the power minus 20. Then you will say, let me first drop the epsilon term and solve the rest of the problem, right? That will be usually what we do with perturbation analysis. If there's some very teeny tiny term, we say just drop it for simplicity. But in things like this, where the highest derivative is multiplied by the small term, small factor, if you drop that, it goes from a second order equation to a first order. And that is a problem because you cannot satisfy two initial conditions or two boundary conditions. So that's the simple thing to remember. In a singular perturbation problem, if you drop the small parameter containing term, you will be more or less correct in most of the domain, but somewhere where you have to satisfy some boundary condition or initial condition, there you're going to be terribly, terribly wrong. So there's going to be one small region where you're terribly wrong. And this is what we found about a vortex. I'll come to that. So like, what is common knowledge? Common knowledge is that particles evacuate vortex neighborhoods. So particles are always leaving neighborhoods where vortices are and collecting in regions of space. So what we say is if you, like, if I'm rotating a stone with a thread, it will go like that, right? It will try its best to reach the highest diameter. So like that, these heavy particles will centrifuge out of the vortical regions, the circulating regions. So this is like common knowledge. And here is a movie by Jason, which shows what happens to particles near vortices. See, you see this gap which is created everywhere, there's a vortex in the flow. So heavy particles just leave the region where vortices are and they collect in regions of strain. So this is what happens. And so, like I told you that the particles are in a compressible flow, right? So I can look at del dot V of the particles. If I can describe it as a field, I can look at del dot V of the particle. So suppose I take a little dabba here, and in the little dabba I am asking how many particles are coming in and how many are going out. Clustering means what? More are coming in and few are going out, right? On an average, more are coming in. Therefore, on an average, del dot V is less than 0. Divergence less than 0 means more coming in and less going out, right? So, on an average, I can say divergence is less than 0. So, in fact, Sapsis and Haller, like many years ago, they actually, for small Stokes number, they did this analysis and they said, this is strain, okay? This is the strain, elements of the strain matrix multiplied by each other. They showed this thing for a particle, for small Stokes number. So this shows that only in strain regions I can have del dot V less than 0. If the strain is not significant, then del dot V will not be less than 0. This is as simple as that for small Stokes numbers. So this is a dogma that particles leave regions of high vorticity, and they go to regions of high strain where they can get it. Similarly, in this region, you'll get del dot V greater than 0. Okay, so this, as I told you, is a singular perturbation problem, and it's highly non-linear because u is a function of x, the flow velocity is taken where the particle is, so it's highly non-linear. It looks very simple, but it's not. It's not as simple. Now, I told you when I look at singular perturbation problems, I can drop the leading term and I can get what is called the outer solution. In our case, the outer solution is sometimes good at large times, and it's never ever good at short times. Even if Stokes tends to 0, you have no right to throw away this term. Now, apart from normal clustering, we are going to ask about extreme clustering, which we'll call caustics. Extreme clustering examples are given here, and in turbulent flows, very often you get extreme clustering in dust storms, in whatever particulate flows you can think about. You will get extreme clustering, and the idea is to understand these things of extreme clustering. They're very important for reproduction. Like suppose these things are living things which sexually reproduce. It's very good for them if they meet other people. And similarly for raindrops, it's very good for tiny raindrops to meet other tiny raindrops to collide and grow. So for many things, this caustics is good. It can be bad for many things also, like in industry, if you're trying to make a powdered fertilizer or milk powder for babies, then if it all clumps up and becomes one big blob, you don't want it. So it can be good or bad, but it's important to understand, right? So like we're going to ask about caustics near the single vortex. We're going to ask, let's just consider one single baby vortex and ask if this kind of extreme clustering can happen. So we realized that, we realized that very close to the vortex, we cannot throw away that Stokes term. We cannot throw away the second derivative term, we have to keep it. But elsewhere in the flow where things are gentle, you can actually throw it away. So we found this out by solving the whole thing, and we can do an analytical analysis as well. And what we call a caustics event is when two things are actually dashing against each other. So two particles with V1, V2 come and dash, and at this place I cannot define a V. I cannot define a V field because there are two V's at the same place, same time. That we'll call a caustics event where this non-field behavior happens. And in this one vortex, Lambosine vortex, and these tiny particles with baby Maxi-Reilly equation, we can actually write down this parameter-free set of two equations. And this is very easy to solve now for us. And we call that analytical, although we've solved it numerically. It's a very simple set of ODEs we got. So we are going to put two rings around the vortex of particles, and we'll say like when two particles are dashing against each other, namely pink is dashing against black and pink is overtaking black, when that happens, caustics happen. So we do this for many different rings all over, and we'll ask, just what is finally the problem we're considering? We've got one vortex which is circulating like this. We've got particles all around, and we're asking when caustics are happening. When the inside one is going to dash against the outside. And that happens only inside a special radius away from the vortex. So this is what we found. So the time for caustics is very short when you're somewhere near the vortex. This is not one in the vortex diads, one in some other area. The time for caustics suddenly diverges. So this is completely an unexpected result. So you can never get dashing, you can never get this kind of collisions if you're far away from the vortex. This is the first result. So whereas the outer solution is just like a simple centrifugation. So this abruptness is completely unexpected. Okay, so then we repeated this exercise for many different particle densities. Extreme clustering means del dot V is going to minus infinity. This extreme level is like all particles from a given volume are actually going to occupy zero volume. So del dot V is going to minus infinity. So we can do this same thing analytically as well, and we can get very similar answers. Then we are going to temporarily move away from caustics, and I'll come back to caustics at the end. But we're going to ask about the basic dogma that heavy particles centrifuge out of vertical region. So that's what we're going to do. And we're going to talk about not just infinitely heavy particles, but particles which are heavy but finitely heavy. So they are heavier than the fluid. We're going to live in that limit where they're heavier than the fluid. So to give you an example, like a raindrop is 1,000 times as dense as air, but this phytoplankton animal, it could be like 1.2 times as dense as air. Microplastics could be very, very similar as water, sorry. And microplastics could be very similar to water. So things in the ocean have very small density ratio compared to things in the air, compared to solids in the air and liquids in the air. So we want to consider such particles which are heavier than the fluid, denser than the fluid, but lighter than infinity. They are finitely dense. So for such particles, the simplified Maxi-Rayleigh will not work. The actual Maxi-Rayleigh equation is very, very much more complicated, and we have to consider that full equation. And we are asking, is it like just this kind of dogma? Is it just that, oh, all heavy particles leave vortices, and am I done with the problem? And like what happens to subsys and Haller's, prove that del dot V is minus something. So we go to an ever so slightly more complex system. Till now we considered one vortex, right? Let's now consider two vortices. And like if there are two vortices, they'll be rolling around each other by themselves, and the particles are all around. So like we'll expect the particles to centrifuge out of that whole place. And then like nothing interesting will happen, no clustering will happen in that vicinity. So is that all that's happening? So we're going to counter the dogma because these two vortices, they form a rotating system. And I can live in the rotating frame of reference, and in the rotating frame of reference, I can like get clustering. This one says that if I'm in the lab frame, I cannot get clustering. But here I'm living in the rotating frame, and based on how fast my system is rotating, I can get clustering even when this frame is not there. It's as simple as that. So this counters the dogma. And I told you we have to consider a much more complicated equation called the complete Maxi-Rayleigh equation. So imagine like just to give you the size or the magnitude of the problem we are confronting. In a cloud, right, every cc, that's this much volume in a cloud, contains in monsoon about 1010 micron droplets. Every cc. And how many cc are there in a meter cube? Already it's like 1 million, right? cc in a meter cube. So it's 10 to the 9, 1 billion particles in this much. Cloud is like kilometers big. So the cloud is going to contain like quadzillion particles. So for each particle, even if it is small, even if it is in one-way coupling, and even if it is in unsteady Stokes, we have to consider this kind of equation to solve it. So you see immediately that this is going to be impossible for any computers, maybe even for quantum computers, who knows. So like we have to devise better ways of solving this, and that we can only do by understanding more about one particle and one vortex, and then we can devise better ways of solving. So this q is the relative velocity v minus u of particle to fluid. It obeys this equation. And just look at this pink terms. The pink terms contain a terrible integral with a root of t minus st is time, and q is this, q dot is the acceleration, and this acceleration at this point depends on the relative acceleration at all historical points in the history of each particle. So like if I have to compute it, I'll be finished. So like we've considered, now I told you there's one more parameter, the density ratio. So r equal to 0 is an infinitely heavy particle, r equal to 1 is a neutrally buoyant particle. So how to solve this very messy equation simply for single particles? This is what my colleague Vishal Vasandi came up with a very bright idea of how to do it. And these two students, past student, Ganga is now faculty in IIT Madras, and Divya is an almost finishing student. So we looked at this problem and we said this thing contains many worries for us. I told you about the computational cost, that's a major worry. If I have to every time do the history, I'm finished. I have to start from zero for every time and keep repeating this integral from zero because this thing lacks the semi-group property. So I can't solve it till some time t and then start the thing. I have to go back to time zero every time. Another thing is like normally you used to Runge-Kutta integration, right? Where you expand in some parameter delta t and you could take terms till delta t square, delta t4, and if I want fourth order Runge-Kutta, I'll truncate at delta t4. So I could write Taylor expansions and cut off where I like, right? But that cannot be done for this problem because you have to expand in square root of t terms. You cannot expand in t, delta t. So I have to work in square root of delta t, and Divya like very brilliantly devised the numerical method, like which is a new kind of Runge-Kutta to do this. And so then like we did something else to rewrite the thing in terms of history. So we rewrite the history in terms of some fictitious K modes, and then we get something like a dynamical system. We actually get a dynamical system with a semi-group property. So this is just a clever rewriting of history without altering facts. So like we now get a dynamical system in a bigger thing. Like earlier we had a V dot equation. Now we have a V dot and an H dot equation, and the H dot is very complicated. But we do this thing and we can actually write this new Runge-Kutta by expanding in root P's, and we get beautiful convergence. And this is the particle rolling out of a vortex with two kinds of accuracies. So we see that we get perfect scaling. So I don't think there's any other numerical method which can do Bassett history so accurately and so well. All other methods are jugaad in some sense or other. So now we'll examine that dogma which Divya and Saumam did. When we have two vortices which are just rotating around each other, they're separated by a distance d, they are identical circulation count. We live in the rotating frame from now on, so the vortices will go nowhere. They will just look like dots because they are rotating, but we are living in the rotating frame. And these are all fluid trajectories. So the fluid trajectories form these things called KAM tori. So they are actually CAM tori which are closed off solutions. So nothing from outside will mix inside, nothing from inside will mix outside. This is what fluid particles do in this rotating frame. This is a well-known thing. But what happens if we have inertial particles with that Stokes number thing I told you? So like they are not zero Stokes number, but they have some reluctance to follow the flow. So these are inertial particles. So when you have heavy particles, we already see that instead of leaving, everybody leaving, many of them, everybody inside this red region is going to cluster in one dot. And they're actually getting attracted towards the fixed point. And note that these are moving fixed points because the fixed point itself is in the rotating frame. So in the lab frame, it's actually going around in a circle. That's why it actually doesn't violate what Sapsis and Haller said, but it is clustering like crazy. So this is actually a formation of a caustics where del dot B is minus infinity. So we have infinite clustering of all these particles into a point-like object. So here basically the basic message is we are seeing situations in the ocean and situations in the atmosphere when things can cluster a lot. And now this goes totally against our thinking about turbulence, right? Like when I put sugar in a teacup and mix it, then like what do I see? I normally see the sugar going uniformly everywhere in the tea. Whereas if I'm putting particles which are uniformly distributed and then I'm putting turbulence, they go into special places. They are demixing. And this is an important thing, like, you know, when lots of bacteria can come into one place or lots of something can come into one place due to turbulence. That's the interesting part. Okay, so like this one, let's skip because we're running out of time. Oh, no, I read the time wrong. Yeah, I can tell you. So every particle who started out near these two vortices will actually go and settle somewhere and never leave this vicinity. They will collect immensely and stay there. As I increase the Stokes number, that tendency goes down really fast, and greater than this mini Stokes number, there's nobody living in this vicinity. It always goes away. And this is for very heavy particles. So the basin of attraction shrinks to zero. Basin of attraction is this thing where all particles starting here will go towards the fixed point. Now, I change the density to another number, and I'm still at, right now I've neglected Basset-Boussinesq crystal. I made a simple maxi ready, and I'm seeing whether the Basset-Boussinesq terms are important or not, whether I need to consider them or not. And you see different types of attractors. There could be a fixed point, there could be a limit cycle of period 2, there could be a limit cycle of period infinity, which basically is a strange attractor or a chaotic attractor. So we draw the bifurcation diagram for this, and you will see like at fixed point till this Stokes number, then limit cycle till here, then 2 limit cycle, the one I'm showing here in this photo, and then like that quickly goes to chaos. There is this thing called the period doubling route to chaos, where like from period 1 it goes to period 2, then period this, then period infinity. It doubles, and the doubling time becomes shorter. Doubling Stokes number difference becomes shorter. There's a Feigenbaum number which we found to be true. And after 0.2455, we see that no particles live in this vicinity. So what I'm trying to say here is, when you had very weak and tiny particles, and they were very dense, they stayed near the vortex, and that was not so much fun. But when you go to lighter particles, like plankton in the ocean, then those particles up to a big size, Stokes number is proportional to the radius square. Up to a finite size, they're going to stay in the vicinity, and they'll keep going in funny orbits, and they have many opportunities to dash against each other. So this is the central message. And you could have never expected something like this to come out when you didn't do this analysis. So like dogma just tells you they all leave. They're all the centrifuge level. So everything you're finding here is against the dogma. Even fixed points, then period doubling route to chaos, everything is against the dogma. So this was without the Basset-Boussinesq history. You put the Basset-Boussinesq history, the chaos disappears. We get only a simple limit cycle, and notice the Stokes number, it's now 0.5. So beyond this, the particles escape, but pretty big particles can live in the vicinity. So this sends one central message: do not neglect Basset-Boussinesq history. Find clever ways of solving it like Divya did, and actually do not neglect it. And so the basin of attraction is very much bigger with Basset history. That's the other thing we find. Okay, so then what happens beyond that Stokes critical? Like here I told you all the particles escape. So is it uninteresting? No, it's not uninteresting, because particles escape, but they could spend a long time in the region, and if they spend long but finite time in the region, that can be good enough for collisions. So like as we change the Stokes number past the critical, you see these very interesting particle trajectories, and in these ridges, you see these ridges and valleys. In the ridges, the particles live for a long time here. And so you see these very interesting patterns, which if I did finite time Lyapunov exponents or stable manifolds, like here I put a stable manifold, I get very similar answers. So this is very canonical behavior in many nonlinear dynamical systems, but nobody expected it in this simple thing of two vortices. And so again, for this, with the Basset-Boussinesq history also, we study how the leaking happens. The leaking happens differently, but it does happen beyond a big Stokes. And the interesting thing is, like, period doubling bifurcations to chaos are very, very normal. Like even in boundary layers, you get some period doubling which takes you from laminar to turbulent. There are situations where you can get period doubling route to turbulence. But period halving, that we could find only very, very few instances. So here you get period doubling, it goes from fixed point to limit cycle to 2 cycle, 2 cycle to 4 cycle, and then it crashes back crashing back to a 2 cycle and then to a fixed point. This is the kind of behavior we get for more heavy particles, more dense particles. And whether it's Bassett or not, we get it at different densities, but we get qualitatively the same answers. So here is one period halving which went all the way to chaos and came all the way back to not chaos. And so with Bassett-Boussinesq history, this one starts looking like a period doubling route to chaos. So like whatever happens without Bassett happens with Bassett, but for bigger particles, for denser particles. So like this is just the summary. This will tell you like how complicated that whole thing is. Like in this place, we got just a simple period doubling route to chaos with this density ratio, and this is Stokes number. And in this density ratio, we got all the way to chaos and then back to simple fixed point. And in this place, we got just a few doublings and then halving again. So very complicated phase plot that you have. And this is the residence times, which are very different. And do I have 5 more? Do you have 5 more minutes for another thing? So all of this we talked about these particles with Stokes number. So we said these are particles who are reluctant to follow the flow. They won't immediately follow the flow. They will show this reluctance. Like suppose, big wave is trying to move a rock. The rock is not going to just follow the flow, right? It's going to show some reluctance. It might finally take the velocity of the fluid, but it's going to go slowly. So these are the kinds of particles we've talked about. We said, what about living things? That's what we call as active particles, because we've got a model for living things. We know that living things cluster, but living things have no Stokes number. Effectively, their Stokes number is 0 and they're in steady Stokes. So what makes them cluster? This was the question we were asking, and these are the co-authors. Rajarshi is a former student of Sriram, me and Narayanan Menon, and he is now postdocing in Stanford, and Rajarshi is a present PhD student. So this is the gang who's looking at this problem, where we're back to the same one-way coupling, same Navier-Stokes equation, same Lambert-Seen vortex, everything same. But we now have the Stokes number going to 0. So these particles are just supposed to be x dot equal to v and v is equal to u. Except that living things don't work like that. For simplicity, we've thrown away this forcing term, and people can ask me later about it if you're interested. But the point is that these things, living things, have this particular tendency, which can be modeled as follows. So you have this spring-like living thing. If the flow is in this, if the strain is in this direction, it stretches. It stretches in response to the strain, and then it has a nose and it follows its nose, or it has eyes and it follows its eyes. So it has a preferred direction. So it's trying to go where its eyes are telling it to go, and so it's not quite obeying this vortex. So it's doing something else, and that is this equation. There are like many models for such living things. One of the simplest is an active Hookean dynamo, which we changed a little bit. We made this respond to the shear with a quantity alpha, and we made this extra term, which I won't have time to explain, but it's also another response that living things do to parabolic flow. So then, when it has this spring stretching behavior, and then the stretchness of it determines that how much it follows its eyes, that is called the activity parameter. That changes the V equal to U story. So like V becomes different from U, and we replace all this in an equation, and we get something like an inertial. We get this term, which is like an artificial mass, which was the Stokes number. You remember the singular perturbation thing we talked about, right? There was this term which we could not throw away, and now we've come back to something like that. Again, it's very non-linear. So we did everything for it near a point vortex, blah blah, and we could actually write this del dot V going to minus infinity expression for it, and find out when caustics will occur. So for living things, I told you, for reproduction, caustics can be very good. For finding food, caustics can be very bad, and things like that. So we show that active particles also, though they have 0 Stokes number, can behave like inertial particles which have a finite Stokes number. So there can be lots of clustering, like this is the number density of these things, and this clustering thing can stay where it is. We showed how caustics occurs, this del dot V going to minus infinity. We showed some scaling for it, and we did proper 2D simulations of these things. So you see that although I showed you that movie of Jason's right in the beginning where vortex regions got cleaned by particles, right? Particles were then collected in strain regions. Something similar happens with these at intermediate levels of activity. So if they're terribly active, they run around and they fill the whole space. If they're very weakly active, they cluster a bit but not much. But in intermediate regimes of activity, they cluster a lot. So that's what happens, although you wouldn't expect them to cluster. So what we're showing here is that they basically go into the strain. If this is the ambient flow, it contains, all this vorticity minus strain in this gray region is in the real flow. At very teeny levels of activity and very big levels of activity, they occupy everywhere in space. But when you go to intermediate levels of activity, they do not occupy the vertical region. This is what this story is telling. And this other parameter, the polar alignability parameter, which I told you about, that enhances this clustering by a lot. And here we just put some real animals who have that level of activity and behave something like the equations that we showed. So we've shown that the number density near one vortex can be very large, and the same story happens in 2D turbulence as well. We've done proper full 2D turbulence, and many of these animals, they start clustering, although dinoflagellates don't cluster. So that concludes my talk. So basically, we've shown that near vortices where nobody is supposed to get trapped, we can actually have large numbers of particles getting trapped. That's if you live in a rotating regime. And this can be important even for planet formation. So in planet formation, you have this cloud of dust in a protoplanetary disk. And these things are by nature in a rotating frame. And because they're in a rotating frame, they are subject to what we found. So they can actually cluster, and bigger planetesimals can form from the dust. So those are also questions which a lot of astrophysicists are asking about how clustering happens to create planets. And this kind of thing that they can actually get trapped near vortices is important for that situation. And we showed that this term, which everybody throws away just because it's complicated, is actually important. They have a reason for throwing it away. They say, oh, we've kept till Stokes number, and this one is Stokes number to the power 3/2. So we are neglecting it because it's higher order. It's only like nominally of higher order, it becomes more and more important. And for light heavy, that means particles like plankton in the ocean, we should not be neglecting basicity. And we found a nice way of computing things with basicity, which didn't exist before. So we actually did a two-step procedure. One is to write this history kernel, and another is to write a new kind of Rangekutta to be able to solve this. And then let's go to the active, the living things we talked about. Our findings we showed only for one equation, but we've actually checked that it's general for several such particle equations. And they can actually, like these living things can mimic inertia. Although they don't have inertia, they can pretend to have inertia, and they can form caustics. And these caustics last for a long time. And in all of these situations, singular perturbation theory can always provide insight. One thing, like I should tell you about the Bassett history, because there's several mathematicians in this group. The interesting thing about the Bassett history kernel, which actually I forgot to mention, I'll just go back to that because there are mathematicians here. Yeah, this thing is actually a half derivative in time. If it's a fractional differential equation, this thing is actually a half derivative in time. And what Vishal said is like half derivatives are so complicated, we always have to solve these horrible integrals. Let's write a fictitious heat equation. The fictitious heat equation being Qt equal to Qxx. We've made up a quantity called x, in which we've written this, and a half derivative in time becomes a full derivative in x. So we've replaced this thing by a full derivative in x. And that's what enabled us to write the history book. So this is just to go back and tell you how that story was done. And I'll just put up my conclusions and oops, thank you for your attention.
Thank you, madam, for giving a talk on clustering of particles in fluid medium, which gives us the behavior of the particles in the flow. Now I request we can just have few minutes, so I can request the participants to ask 2 or 3 questions. Otherwise, you can interact during the lunch session. Now we have the lunch break. So madam is available in the lunch session and you can interact with me. Thank you, one and all.
Thank you, ma'am, for your wonderful talk. So we request Professor Rama Govindarajan, ma'am, to accept a small token of gratitude. I request Professor H.P. Rani, ma'am, to present a memento to ma'am. I request Professor Aditi Suresh Babu, sir, to join. Thank you all. So I request all of you to join for the lunch. It is arranged at faculty club. So then there are sessions which are located at post hall, lecture hall complex.